You build an agent, you ask it to do something, it does a decent job, you are happy, then tomorrow you ask it to do the same thing again, but it starts completely from scratch. It has no idea it ever met you, it redrive everything from scratch and also rethink about everything figured out already yesterday. It pays the full price in tokens and in time for a knowledge that already has been produced once. So in this video, I'm going to fix that. I'm going to give an agent a real memory, one that survives across runs, that lives on disk, that gets smarter the more you use it. And I'm going to do the whole thing locally. No OpenAI key, no cloud bill, nothing leaving my machine, just a DSPy for the reasoning, Mem0 for the memory, and Ollama running the models on my hardware. I'm going to put a live dashboard on screen and we are going to watch the savings happen in real time. Memory calls, model calls, cache hits, and estimated cost saved, all ticked up live while the system works. So let's build it. Let me describe the whole system first before going into the code. We have a stream of tasks. Think of it like a content team building a course. Write the outline, write the quiz, write the lab, write the FAQ, and so on, over and over. Every single task does the same thing. First, it asks memory. Have we done something like this before? What do we already know? Then, based on the answer, it makes a decision. If memory is basically empty for this task, it does the expensive thing. It plans, then executes, and do all the LLM calls. But if memory already has solid context, it takes a shortcut. Maybe only one model call that just updates what we already know instead of regenerating it from zero. After the task finishes, we write the result back into memory. So the next task is a little smarter than this one. And on every task, we quietly record what happened, how many memory calls, how many model calls, how many tokens we think we spent versus what we would have spent without memory. That recording is what feeds the live dashboard. So the big idea is a loop. Memory feeds the decision feeds the work feeds memory. And the whole thing feeds a dashboard that proves it's working. And that's it. Everything else is just careful plumbing. So here is a project layout. So we have the config and utility files, and also we have three modules: pipelines, telemetry, and workloads. Pipelines module is a brain. That's where the actual reasoning lives. Notice there are two of them, memory pipeline and no memory pipeline. That pairing is deliberate. One uses memory, one doesn't, and they share the exact same task definition. So when we compare them, it's a fair fight. Telemetry is a nervous system. It records what happened and it draws the dashboard. The recording and the rendering are separate files on purpose because writing number down and painting picture of numbers are two different concerns. Workloads module is the engine. It's what generates pressure. It runs task after task after task, so we actually have something worth measuring. And then the config and utility files at the top are the shared foundations that everybody else stands on. So the structure is being split this way because the moment we want to add a new orchestration layer or library like ChromaDB, which what we will be doing in the next videos, you don't want to untangle 1,000-line file. You just want to drop a new pipeline into the pipelines folder and reuse the same telemetry and the same workload. Okay, so now we can have a look about the architecture of the system or the structure of the system. So it starts with the task stream on the left. That's just a list of jobs we wanted to be done. In our case, it's a course building tasks, but mentally you can replace that with support tickets, research question, code reviews, anything repetitive where yesterday's work should help today's work. That stream feeds the workload runner. The runner is the conductor. It doesn't do the thinking itself. Its job is to pull the next task, push it through the pipeline and keep time. It's the thing that turns one task into 1,000 tasks over 10 minutes, which is what we need if we want a graph that actually moves. Now here's the first interesting move. Before we ever call a language model, we go to Mem0 and we do the search. This is the part which is interesting and it's the most important part. We are asking the memory layer, what do we already know about the relevant information for this task? And Mem0 doesn't just dump a keyword lookup. Under the hood, it's blending semantic similarity, keyword matching, and entity matching, then ranking the result. So what comes back isn't raw text. It's the most relevant slices of everything we have ever learned, already sorted by usefulness. Then we hit decisions diamond, and this is the heart of the whole thing. We look at how much relevant memory came back. If we got real coverage, if memory clearly already understands this task, we take the first pass, a single model call that just updates and refines what we already have. But if memory came back thin, if this is genuinely new territory, we take the deep path. Two model calls, one to plan the approach and one to execute it properly. So here, there's one thing I have to be clear about it. The savings here don't come from the caching. We are not replaying old answers. The saving come from doing less work when less work is justified and full work when full work is needed. That's the difference between a system that's merely fast and systems that actually smart about when to be fast. A cache would say, I have seen this exact thing, here's the old answer. But using Mem0 or using memory system, the answer will be something like, I understand the neighborhood of the problem, so I can take shortcut while producing something fresh. That distinction is the whole game. So both passes then coverage and write their result back to Mem0 with the add functionality. This is the feedback arrow. Every task we finish makes the memory richer, which makes the next decision sharper, which makes the next task cheaper. It's a flywheel. Underneath Mem0 sits ChromaDB on disk. The on disk is doing a lot of quiet work. It's the reason memory survives when the process dies. You can kill the program, walk away, come back tomorrow, start it again, and it remembers. Without that, you would have clever in-memory cache that evaporates the moment you hit Ctrl C, which is exactly the problem that we are trying to solve. And running alongside all of that, the telemetry path. Every task, the runner also hands a little structured record to the telemetry logger. How many memory calls, how many model calls, the token estimates, which path we took. That gets written to a single JSON file. And the dashboard reads that file on a loop and draws it. The reason telemetry is a separate arrow and not packed into the pipeline is that I never want measuring the system to change the system. The work happens and the recording of work sits politely off to the side. So now let me zoom into a single task and explain it a little bit deeper, because once you see one task clearly, you understand all of them. We will walk through this task step by step. It begins when the runner takes the task and immediately turns to Mem0 and searches, and notice what's attached to that search. Filters, especially user ID and agent ID. That's not decoration. In any system that more than one person or more than one agent touches, unscoped memory is a data leak waiting to happen. If I don't filter, my agent could pull back somebody else's memories, or one agent's nodes could pollute another's. By scoping every search to an identity, retrieval stays both relevant and safe. Think of it as memory with permissions built in. Mem0 answers the ranked memories and implicitly a count of how many we got. That count is a signal. It's small, but it carries the entire decision. Next, still inside the runner, we decide. No model is involved yet. This is a pure sheep local logic looking at how much memory came back. Did we get real coverage or did we get crumbs? That single question routes us down one of two roads. Then we actually call the model, once if we are on the fast path, twice if we are on the deep path. This is the only expensive step in the whole sequence, and that's exactly why every cheap step before this point is in service of making this expensive step as small as it's allowed to be. The model hands back the output, and now we need to call add and attach the metadata, which session this was, which task, which path we took. So the metadata is useful because future we will want to ask question like show me everything from this session, for example, or how often did we take this path on this kind of task. We can only answer those questions if we wrote the labels down at that time. Metadata is a note you leave for your future self. And finally, in parallel, we log the number to telemetry and the dashboard, which is just sitting there, refreshing every couple of seconds, picks up the change and redraws. So here's the thing that I want to explain more. In this sequence, memory is both an input and an output. We read from it at the start and we write to it at the end. That's what makes it a life cycle and not a pipeline. A pipeline goes in one direction and forgets. A life cycle loops back and accumulates. The first task in a fresh session is dumb and expensive because memory is empty and every road is a deep road. But task 50 is sharp and cheap because by then memory has seen the whole neighborhood and the fast pass starts winning more and more. The system is, in a very literal sense, learning on the job, not by retraining a model, but by remembering its own work. All right, now we go into the code. So we start with the config.py because this is the file that wires the whole machine to its engine. Everything else assume this run first. So we import the important packages, the warning and the Mem0 and the memory from the Mem0 and the DSPy. For the warning, we have to filter the warning here. This little block is a pure quality of life. One of our dependencies deep down throws a specific deprecation warning that we can't fix and that has nothing to do with us for now. So I silence that once exact message happened. Not all the warning, just this one matched by the exact text you will see here in the message, just to have our console output a little bit clean and see the other signals, the other important signals that we are looking for. Then we set the Ollama base URL and we have to set the Mem0 configuration. So Mem0 configuration is a dictionary with three parts. The first part is LLM. Mem0 uses its own language models separately from your app's model. So when you save something to memory, Mem0 doesn't just dump your raw text in. It runs through a model to extract the clean atomic facts worth keeping. So this model right here is the one doing the extraction. And if we look at the temperature, it's 0. That's intentionally, and it's important. Extraction is not a creative task. I want the same input to produce the same facts every single time, deterministically. Temperature 0 means no randomness, no surprises. The model that writes your marketing copy should be creative. The model that describe what to remember should be consistent. And we can set the max token and the Ollama base URL. The second part, the embedder, this is a different kind of model. Its only job to turn text into vectors, long list of numbers, so that we can search by meaning instead by exact words. So this what makes find me memory similar to this task actually work. When you search Mem0 later, this is the model that powers the semantic part of the search. The third part where the memories actually lives, we are using ChromaDB. The collection name is just a label for this patch of memory, like a table name. And here I just want to store it locally in project folder. That's a folder on disk. And then we hand off all this configuration to the memory and create the memory object for us. And finally, we need to set up the model that our actual pipeline use for the DSPy, using the DSPy library. So this will be separate from Mem0's extraction model, as we saw in the previous video. So here just a normal configuration for DSPy using the model, the local Ollama model, supplying the API pairs, the temperature, and the max tokens. Next, we have the utility files. This is a junk drawer in the good sense, small shared helpers that everybody uses and nobody wants to rewrite. So we have a few standard imports, and then we have the path for our runs.jsonl. The JSON extension means JSON lines, one complete JSON object per line. It's lovely format for logs because you can keep appending it forever without ever rewriting the file, and you can read it back one line at a time. So the first function here, ensure dirs. This is a little function, just make sure our folders exist before we try to write into them. We have here the data, the artifacts, ChromaDB. The second function, we have rough token count. This is just estimation, not a real one. The rule of thumb is that one token is about 4 characters of English. So we take the length of the text and integer divide by 4, and having here the max just guarantees we never report zeros. We are running locally on Ollama. Llama doesn't build, so there is no usage meter to read. But we still want numbers that moves dashboard and see how much exactly we are saving or how much exactly we are consuming. If we are running this against a real paid API, you would swap this out for the provider actual token usage from the response itself. For the demo about relative saving, the approximation is completely fine. So we have the log run here function This appends one run to our log file. It makes sure that the folder exists, open the file in append mode, turns our record dictionary into JSON string, and writes it on its own line. So now we have two tiny functions here. Now TS gives the current time in number, and file exists is thin wrapper for checking the path. So now we get to the interesting part. So in the pipelines module, we have the signatures module, and here's the mental shift. In most code, you write a prompt, a big paragraph of instruction. In DSPy, you instead declare the shape of the task. Here are my inputs, here are my outputs. Here's a one-line description of each, and DSPy then builds the actual prompt for you behind the scene. You are describing the contract, not handwriting the prompts. We already had a deep dive in one of our previous videos. You can see the link in the description below for the DSPy explained video and also the DSPy short intro video. So the first class we have here is a gap planner. So when we read the doc string, which is not actually a comment, DSPy actually uses it as a task instruction. This signature takes two inputs, the topic we are working on and known facts, which is whatever we pulled out of memory. And it produces one output, open questions. So in plain terms, this is the step that says, given what we already know, what actually don't we know now? It's a gap finder. It's how we avoid researching things we have already nailed down. It explicitly steers the model towards the holes. The second class, the researcher, takes the topic and those open questions and turn them into findings, actual answers. Notice it takes the open question as input. That's a chain. The planner found the gaps, and now the researcher fills exactly those gaps and nothing else. The description even asks for non-overlapping findings because we don't want it repeating itself. And the last class, synthesizer, is a closer. It takes three things, the topic, the old memory, and the new finding, and merges them into one clean report with no duplicates. This is where old and new come together into a single coherent answer. The other module, no memory pipeline, this is the simpler of the two, and it's our control group. It's our baseline to measure against. We import here all the important libraries and modules that we will use, and we get the previously defined DSPy classes for the signatures. And we have now our first class, the no memory pipeline. So we define this as a DSPy module. That's a DSPy base class for things that made of steps. In the constructor, we wrap each of our three signatures in DSPy predict. So predicts what turns a signature, which is just a description, into something you can actually call like a function. So now self.plan, self.research, and self.synthesize are three callable steps ready to fire. We have the forward method, which is a method that runs when we call the pipeline. We grab a start time so we can measure how long the whole thing takes. And then this is the defining line of the entire file. So here we have just a variable. Just say that there's no prior memory. It's just a defining way for our no memory pipeline to say that this pipeline is not taking any memory in consideration. So it works in every single time with a completely blank state. And we have the plan. So the three steps run in a chain. We plan, feeding in our plan key memory. We take the plans, open question, and research them. And then we synthesize the topic, the blank memory, and the new findings into report. So you can watch out how the output of each step is flying as an input for the next step, like from getting from the plan, the result, feed it to the research, and then get whatever in the research, feed it back to the synthesize step. So here we just measure and record. So we glue our input together into one blob and our outputs into another, just so we can estimate tokens for each side. Then we build a record. The mode is stamped, no memory pipeline. So later we can tell our two pipelines apart in the log. Latency is now minus start, rounded, and notice the giveaways of the control group memory hits is 0 and recall charge is 0. And also the novelty ratio is 0 because with no memory there is nothing to hit, nothing recalled, and nothing to compare new work against. So we log it and return it. Finally, we have the main function, so we can run the file on its own. It builds the pipeline, pick a topic, runs it, and pretty prints the result. So in the other pipeline, the memory pipeline, it's actually the no memory pipeline plus brain, and it talks to memory at both ends. So we start by importing the important libraries and also the signature from our pipeline signatures, mostly the same import like the previous one. And here I defined the run matrix data class. A data class is just clean way to define structured bundle of fields. I'm doing this because the matrix here are richer than in the baseline, and I want them to have fixed name, shape, latency, memory hits, recalled characters, two token estimates, and novelty ratio. Forcing schema like this means I can't accidentally typo a field name or forget one. So now for our memory pipeline, the constructor takes three things the baseline didn't, which is the user ID, agent ID, and the top K. The first two are our memory scoping, the identity tags that keep the agent's memory separate from everyone else. Top K is how many memories we will pull back at most, defaulting to 8. Then the same three reasoning steps as before. So structurally, it is the baseline plus an identity and retriever budget. So the method for the search memories is a retriever method. So we call the memory search with the topic and our identity filter and the limit. Then there is some defensive handling, and I want to explain why it's there because it looks fuzzy. If nothing comes back, we return empty list, clean, but different versions of Mem0 returns the result in slightly different shapes. Sometimes it's dictionary with results key inside. Sometimes it's already a plain list. So we check if it's dictionary, dig out the results, otherwise use it as it is. And here the format memory is just helper function, turns the raw memory object into clean text the model can read. If there's nothing, we return the same, no prior memory. And that's a nice touch because it means an empty memory pipeline produces the exact same context as the no memory pipeline, which keeps the conversion honest. Otherwise, we loop through each memory, pull out the text, skip any blanks, and format the rest as a bullet list. So what comes out actually is what we will feed into the planner. It's the same like we are telling here's what you already know. Then we compute the novelty ratio, which is a number representation of how much new results or new stuff we found versus the one that we already had. So if there is nothing new, novelty is 0. Otherwise, we count the overlap subtracted from the new total and divide. So 1 means everything was fresh, and a number near 0 means we mostly repeated ourselves. This is a cheap, transparent proxy answering the question, is memory making us redundant or are we still adding value? It's not a perfect semantic measure, it's just a line based, but it's honest and you can see exactly how it's computed. Now the main flow, so we have here the function forward. We start the clock and then unlike the baseline, the very first thing we do is search memory and format what we got. This is the input side of the memory loop. We walk in informed instead of blank. The same three-step chain as the baseline, so plan, research, and synthesize we are implementing here. And we add to the memory, here is the output side of the loop, the line that makes the whole thing compound. We take the final report and write it back into memory, tagged with our identity and some metadata. Now the next run on related topic will retrieve this. This single add call is the difference between system that learns and system that forgets. Then we measure, and now the metrics are alive. Memory hits is the actual count of memories we pulled. Recall charge is how much context we got back. Novelty is computed from real old versus new. Compare this to the baseline where all of these were flat zeros. This is where the comparison happened. We assembled the record, stamped memory pipeline this time, so it is distinguishable in the log, including the identity field. We turn our matrix data class back into plain dictionary, so it serialized cleanly to JSON, log it, and return it. Same logging path as the baseline. So here is the main function. So it's the same like what we saw with the no memory pipeline. So we just initialize the memory pipeline, pass the identity fields, the user ID and agent ID, and then we just call the pipeline and dumps out the output. For the telemetry, we have this live telemetry module. And here's a part that records what happened. This file doesn't make any single LLM model call. It just keep track of whatever being logged. So we have the initial import for all packages and setting up the path for the matrix. The lock is the threading lock because writing to a file isn't automatically safe if two things writing at once. The lock guarantees only one writer touches the file at a time. So we never end up with a half-written corrupted mess. So we have two helper functions, ensure data there and atomic write JSON. Ensure data there, just make sure the folder is there. And the atomic write JSON is the clever one. Here, instead of writing directly to our real file, we write to a temporary file first, and then we replace the real file with it. And this happens because replace is atomic at the operating system level. It happens all at once or not at all. So our dashboard, which is reading this file constantly, can never catch it mid-write. It either sees the complete old version or the complete new version. And here I have just a helper function to reset the live matrix. And this will reset everything to clean state, start with the session. We have here also the read live matrix. This reads the file back. If the file isn't there yet, we return an empty dictionary instead of crashing. And if somehow we catch it in a bad JSON state and JSON cannot be parsed, we also return empty rather than blowing up. We have this helper method here, the estimate cost USD. This converts the token estimation into dollar estimation using a blended rate of 0.4 of a cent per 1,000 token. This is just for us to have some kind of pricing in our dashboard and something to compare with the pricing for LLM calls. For the log task event, here I think this is the busiest function in this file. It's called once per task, and it folds that one task numbers into the running totals. We take the log, read the current state, and then do the work safely with the numbers. So we pull out the task's path and the actual token estimation and the baseline token estimation. So here we are trying to answer what is the cost without memory. Saving is simply baseline minus actual. So here we just need to pull the task path and then have the actual token, the baseline token, so the token without using any memory techniques. And then we have the saved token, which is the baseline minus the actual tokens. So this will be the number of tokens that we saved using the memory versus using a pipeline without memory. And then we continue. We just have all this kind of calculation for the totals that we are doing here in this telemetry. And just the same idea goes on by on. So we are trying always to have this kind of estimation of the saved calls and also the actual number from the memory pipeline and the baseline number and so on. So here we have the final function, which is a mark complete. The last function just flips the status to completed when the session ends. That's what lets the dashboard show green done badge instead of still running one. Small thing, but it closes the loop cleanly so anyone glancing at the screen knows the run is finished. For the workload part, I just have here one module to run everything with some kind of heavy queries or heavy consumption for our pipeline, just to push our pipeline to the limit. So the dashboard with one data point is a sad dashboard. This file is what generates real sustained pressure, like task after task after task. So the graph actually will have a story to tell. Like always, we start with just importing the important packages and modules. And then we have three classes, three signatures. And these encode our two-speed strategy directly. So we have the plan task and execute task, which are the deep path. First plan, then execute, two model calls for genuinely new work. The quick task is the fast path, like a single call that take what memory already knows and just update the deltas. The work item class is just the ID paired with the task description, and then we define 8 of them. And these aren't random. They are all about building one course on transformer attention. That shared theme is a secret ingredient because every task lives in the same world. The memory from the outline generally helps the quiz, which helps our FAQ and also helps the capstone. They overlap on purpose, so memory has something real to contribute. If I had picked 8 unrelated topics, memory would rarely help and the whole demo would fall flat. The realism is what makes the saving show up. And then we have the runner class, the heavy usage runner. The same identity and budget setup as the memory pipeline, user ID, agent ID, and the top K. Then it wraps all three of those signatures into callable step, plan, execute, and quick. So this one object holds both gears, the deep one and the fast one, ready to pick between them. So here the search memory and format memory is the same that what we saw in the memory pipeline. So we have the scoped search with the same defensive shape handling and the same bullet list formatting. Now the core, running single task. For example, we search a memory, format it, and count the hits. Then we set the baseline at 2 model calls with a comment explaining why the baseline is a no memory word. And in that word, you will always do the full deep path, 2 calls every single time. And here for the memory add, whichever path we took, we write the result back to memory, closing the loop again with rich metadata. The session, which task, and which iteration, and which path we chose. And here we have the estimation, the actual blob, including the real memory context we use, and the baseline, the base blob. So here we have for the event, all the important fields that we need to package it together for that session. The run live session is which drives the whole session. So we have a unique session ID here, and with a short random suffix, reset the telemetry to 0 for the fresh run, and build our runner with a real identity. Then we record the start time, convert our duration from minutes into seconds, and start an iteration counter at 0, and then we are about to loop. Finally, we have the main function, which is read to commands line option, how long to run, defaulting to 10 minutes, and how long to pause between tasks. So this module is about just having a script so we can test the memory and no memory pipeline setup in some kind of robust behavior without using our actual pipeline that we designed earlier, but just to have some kind of sense in our dashboard how this kind of heavy task could be running and what we can see in the dashboard as a difference. In the project YAML file, I put some commands from Poetry to help me run my application fast. So I have the demo no memory, which will call the no memory pipeline. I have the demo memory, which will call the memory pipeline. And this what makes it easier later on when just running the command Python run demo dashboard or Python run demo no memory, then it will just call the respective pipeline. So for the demo, we'll start here by making sure that the dashboard is clean. So we start by typing the command demo reset. So this will just reset all the dashboard metrics and all the telemetry data that we collected before. And we need to start a new terminal. In that terminal, I will just run the dashboard as a side task. So here, Poetry run demo dashboard. And here we just see the yellow warning. There is no data from any running task. And going back to the first terminal, we can run the first demo, which is a no memory demo. So Poetry run demo no memory. And if we look back in the dashboard, we see now we already run one task and we had a 3 LLM request for this task, and this is a no memory pipeline. And of course, no matter how many times we try this pipeline, there would be no memory hit. We can test it again. We can see here in the dashboard again, we tested the same pipeline, which have the same question and same topic, and still we didn't get any memory hit. We always have the 3 LLM request with the full cost compared to the baseline, which is actually the no memory pipeline is the baseline. But if we try to run the memory pipeline, the first time will be similar to the no memory pipeline. So there will be no memory hit. And I see here that this command already finished. So we go back, we see the memory pipeline already recorded here. There is no memory hit because this is the first run. But if we run it for the second time, we can go back and we can see here the second call for the memory pipeline. We already start to get memory hits. In the task, the number of memory calls, the number of memory hits that we get from our just last call. And here's the total number of pipeline that we already executed. We executed 2 times the no memory pipeline and 2 times the memory pipeline. And we can see here, starting from the third run, which was the memory pipeline, we start to see increasing in the memory hits, because the first one was a memory pipeline and we already got some hits from memory. And yeah, here just a count of the number of pipelines that we run. We have the fast and deep from the workload that we saw in our implementation. But for now, I run the no memory and memory pipeline because it will be obvious to see the more that we run the memory pipeline, we start to get more memory hits and we actually start to save some tokens. So what we did so far, so we didn't just pull the vector database onto an agent. We built a small system with a point of view. It asks what already it knows before it works and decide how hard to work based on the answer. And it writes down what it learned so it's smarter next time, and it measures every bit of that. DSPy gave us clean, composable reasoning steps instead of a wall of prompt text. Mem0 gave us real memory extraction, scoping, and smart retrieval instead of a dumb cache. Ollama kept the whole thing local and free, and the telemetry layer turned "trust me, it's faster" into a dashboard you can point at. Thanks for watching. If you want more of this, like the video, subscribe with the notification on, and share it with your friends. We release new videos every week on AI development, agents, and developer tooling. Thanks for being here.